There's a heaviness to being still. You notice it most when you stop moving, really stop. The kind of stop that happens only in a bed, in the dark, when the day has finally run out of reasons to continue. The body sinks, not dramatically, just a slow, quiet surrender to whatever is beneath you. And in that stillness, something keeps going. You do. Not your thoughts, not your breathings, though those too, but you, the whole physical fact of you, is moving through something right now. Has been all day, will be until morning. You've been so focused on moving through space that the other thing, the one that never stops, that requires nothing from you, that costs no effort and allows no pause, has just been running in the background, unacknowledged. You're moving through it. Right now. I know that sounds like the kind of thing someone says to be interesting at a party. Time is a river, man, but that's not what I mean, and I want to be careful here not to let this slip into something vague and comfortable. This isn't a metaphor, this is physics. The specific, measurable, embarrassingly literal fact that your body, this mass, in this gravitational field at this speed, is aging at a rate that is not the same as the rate of someone sitting in a different place, moving at a different speed, positioned at a different height above the Earth's surface. Not symbolically different, actually different. Detectably, instrumentally, write it down different. That used to seem insane to me. I used to think, and I held this assumption for longer than I'd like to admit, that time was the one thing everything shared equally. Space could vary, distances could compress, speeds could differ, but time was the fixed rail the whole universe ran on. Same for everyone, same everywhere. It isn't. The place where this starts to crack open is something called time dilation. And I'll get to the details of it in a moment. Actually, the details are the point. But before that, there's a feeling worth sitting with first. The feeling of what it means that time is structural, that it bends, that it is not a property of the universe the way a rule is a property of a game. It's more like a physical thing, something with texture, something that responds. Einstein figured this out or rather derived it, which is a different kind of knowing, in 1905, when he was 26 and working in a patent office in Bern. There's something mildly annoying about that detail, the genius in the mundane job. But it matters here because the insight didn't come from an observatory or a particle accelerator. It came from thinking. Hard, clean, careful thinking about what it would mean if the speed of light were constant for every observer, regardless of their motion. If that's true, if light always arrives at the same speed whether you're running toward it or away from it, then something else has to give. And what has to give for the math to hold together, is time. Time has to flex. It has to slow down for moving things, speed up for things sitting in weaker gravity, adjust itself continuously so that the speed of light stays fixed. That's the deal. Light gets the constant. Everything else negotiates. Here's what that actually means for you tonight, in this room. Your head is slightly farther from the center of the earth than your feet are. Maybe 40 centimeters. Maybe less if you're lying down flat. Doesn't matter much. There is still a difference. And because gravity weakens with distance, and because weaker gravity means time runs marginally faster, your head has been aging very, very slightly and more quickly than your feet your entire life. Not enough to measure with anything you own, but enough that the difference is real. Enough that if you could somehow compare the age of the atoms in your skull to the atoms in your heels, you'd find them at slightly different points in time. Your head is technically older than your feet. I keep turning that over and it doesn't stop being strange. It should get less strange the more you look at it. It doesn't. Now take that principle and scale it up. Pull it out of the bedroom and put it into orbit. There are 24 satellites circling the Earth right now, part of the GPS constellation, each one carrying an atomic clock so precise it would take 30 million years to gain or lose a single second. These clocks are remarkable pieces of engineering, stubborn, obsessive timekeepers, and they are wrong, not because they're badly made, because they're fast. Each satellite is moving at roughly 14,000 kilometers per hour. At that speed, special relativity says its clock should lose about 7 microseconds per day compared to clocks on the ground. Time dilation due to velocity, the fast-moving thing aging slower. But the satellites are also orbiting 20,000 kilometers above the surface where gravity is weaker, and weaker gravity means time runs faster. That gravitational effect adds back 45 microseconds per day. Net result, the satellite clocks run fast, about 38 microseconds per day ahead of the clocks on the ground. 38 microseconds. It sounds like nothing, and it would be nothing except that GPS works by measuring the time it takes for a signal to travel from a satellite to your phone. Light covers about 11 kilometers in 38 microseconds, so if you don't correct for this, if you just ignore Einstein and let the clocks drift, your GPS would tell you you're 11 kilometers from where you actually are. And that error compounds. After a day, 11 kilometers off. After a week, you're being directed into fields, rivers, the wrong country. The engineers knew, they corrected for it. Every GPS receiver on Earth is running a quiet relativistic correction right now, compensating for the difference between time up there and time down here. Your phone is doing Einsteinian physics every time you ask it for directions. You've been navigating through a relativistic universe your whole life. You just had a little help. But here's the thing I keep coming back to. The thing that makes this more than just an engineering footnote. It means time travel is not a question of whether. It's a question of how much. The astronaut Scott Kelly spent 340 consecutive days on the International Space Station. When he came back to Earth, he had travelled into the future just barely, measurably, certifiably, relative to his identical twin brother Mark, who had stayed on the ground. They share the same DNA, started the same age, left the same starting line. One of them moved through time slightly faster than the other, and it wasn't Mark. They measured it. It was real. It was small, of fractions of a millisecond, but the instruments are honest things. And the instruments said, this person is slightly younger than that person, and they were the same age when they started. Scott Kelly time travelled to the future. By being in orbit for a year, he didn't feel it. He didn't experience a flash or a threshold or a moment of arrival. He just came back, and the clocks, which are more patient than we are, had kept the score. So when we ask whether time travellers are already among us, the obvious answer, the one that is easy to gloss past because it doesn't involve wormholes or glowing portals, is yes. There's one every time an astronaut returns from the ISS. There's a version of it every time a high-speed particle is fired through an accelerator and observed to decay more slowly than it would at rest. We've been watching things travel in time. We're just better at noticing it when it's dramatic. What we haven't done is go the other way. That's the harder direction, the one where the math starts to get uncomfortable. The one where Einstein's equations, pushed into certain extreme conditions, start producing geometries that even their inventor found disturbing. Forward is easy, or at least possible, and proven. Backward is where it gets strange. 3 of us work on this. Every script, Every frame, every hour of research that ends up in a single quiet sentence. No studio, no budget, no one paying for the lights. If something here made the night a little more interesting, you can help keep it going over on Patreon, completely your call. But it genuinely means the difference between continuing and not. There are people who already do, who show up there each month and make this possible, and we're grateful for it in a way that's hard to put into words without sounding like a speech, so we won't. Just thank you. That's the whole of it. The sleepy physicist keeps going because enough people have decided quietly that it should, and that's a strange good thing to be on the receiving end of. Backward through time. We're going there next. Not because it's confirmed, not because anyone has done it or even designed a machine that could, but because the equations haven't said no, not cleanly, and in physics that incomplete silence is worth following. It's the not quite no that makes the next few hours interesting. October 1971. Two physicists, Joseph Hafele and Richard Keating, packed 4 cesium atomic clocks into commercial airline seats. Not cargo. Seats, they bought tickets for the clocks, paid for them like passengers. The clocks flew eastward around the world, then westward, and when they landed and were compared against identical clocks that had stayed on the ground, the numbers were different. That's the whole experiment. Start there, because what I want to think about isn't the result, then not yet, but the image of it. 4 atomic clocks in economy class. Somewhere over the Pacific probably, the cabin dark, most passengers asleep, a tray table folded down and on it, or near it strapped in, running, a machine that could measure time to within a billionth of a second, keeping its own private record of the flight, not caring about turbulence, not caring about the altitude or the pressure differential or the meal service going past, just counting with a patience and an exactness that no human timekeeper had ever managed. There is something quietly relentless about an atomic clock. Fussy, actually. Fussy in the way that a very good instrument is fussy, not fragile, just uncompromising. It doesn't round, it doesn't approximate. It holds the line on time with a kind of blunt stubbornness that makes every other clock in the world look like it's just doing its best. Hafele and Keating were testing a prediction. Einstein had mathematically derived decades earlier that a moving clock would run slower than a stationary one, and that a clock at higher altitude, where gravity is weaker, would run faster. Both effects at once. Pulling in opposite directions, different magnitudes depending on the direction of flight and the speed. The eastward plane flies with the Earth's rotation, so it moves faster relative to a fixed point in space, meaning more velocity-based time dilation, meaning the clocks lose time. The westward plane flies against the rotation, slower relative to that same fixed point, less velocity dilation, more gravitational gain. They predicted specific numbers, small ones, nanoseconds. They flew the clocks, they compared. The clocks agreed with Einstein, not roughly, not in the right general direction. They agreed within the margin of experimental uncertainty, which in 1971 was already extraordinarily tight. The eastward clocks had lost 59 nanoseconds. The prediction had been 57 plus or minus 10. The westward clocks had gained 273 nanoseconds. The prediction 275 plus or minus 21. You can spend a long time looking at those numbers. I used to think, and I'm not sure when exactly I stopped thinking this, it sort of dissolved rather than broke, that experiments like this were about confirming something already known, that the value was in the reassurance. Einstein was right, good, violet away. But that's not what's happening in an experiment like this. Not really. What's happening is something more unsettling. The clocks weren't proving a theory. They were proving a world. There's a difference. A theory is a description. A world is a place you live in. And what Hafele and Keating did, with their bought airline tickets and their cesium beam timekeepers and their careful comparison on the ground afterward, was demonstrate that the world you live in has a specific, measurable, structural relationship with time. That time is not the same everywhere, that it was never the same everywhere, that every clock you've ever seen was running at a rate determined by where it was and how fast it was moving, and that this has been true since before anyone built a clock to notice it. The universe was already doing this in 1971. It was doing it long before 1971. It has always been doing it. The experiment didn't create the phenomenon. It just finally made it legible. Here is the part I find hardest to sit with, and I want to be honest about that rather than gloss over it. If time runs at different rates in different places, and it does, this is not a hypothesis anymore. It is an observed and confirmed and GPS corrected fact of daily life. Then the word now is doing something strange. When you say right now, you mean a specific moment that is simultaneous with this one. But simultaneity, it turns out, is not a global property. It's local. It depends on where you are and how you're moving. Two events that are simultaneous from one frame of reference are not simultaneous from another. Einstein called this the relativity of simultaneity, and it's one of those things that the more carefully you look at it, the less stable the ground feels. Not because it's paradoxical, it isn't. It's internally consistent, it's precise. The mathematics handles it without flinching. But the implication that now is not a universal slice across all of existence, that the present moment is not a shared thing but a local one, specific to each observer's position and velocity, that implication has a weight to it that doesn't really diminish with familiarity. Or maybe it does for some people. Maybe physicists who live with this every day have found a way to let it sit quietly. I haven't quite managed it. But here's what the Hafele-Keating experiment does that the theory alone couldn't do. It makes it ordinary. 2 men and 4 clocks on a commercial flight. The kind of flight where the seats are slightly too small and the air is recycled, and somewhere in row 20-something, a child is intermittently kicking the seat back of the person in front of them, and nobody's really sleeping well. That kind of flight. And in the middle of that completely ordinary, slightly uncomfortable, mildly tedious human experience, time was running at a different rate than it was on the ground. Not because the plane was special, not because the instruments were magical, because that is what time does when things move. The mundane wrapper around the experiment is not incidental. It's the point. Relativity isn't a condition that activates only in extreme environments, near black holes or at the edge of the solar system. It's running right now in the background at every speed and every altitude on Earth. You just don't have instruments sensitive enough to feel it in your body. The clocks do, and they've been politely keeping the record of it ever since. What the experiment couldn't tell you, and this is the constraint I keep returning to, is what it would feel like to be the clock. The cesium atoms didn't experience the flight differently. There was no sensation of slowness, no awareness of the discrepancy accumulating. The deviation was real, but it was silent, invisible from the inside. The clock that ran slow didn't know it ran slow. It was just doing what physics required of it in those specific conditions, ticking along at the only rate available to something moving at that velocity, at that altitude, through that particular region of space-time. Which means, and this is the part that loops back to where we started, that you can travel in time without knowing you're doing it, without feeling a threshold, without a portal, without flash, without the narrative machinery we've all absorbed from fiction. You just move, or you stay still, and time, pliable, structural, local, slightly different in every location, responds accordingly. You've been doing it your whole life, at a rate almost impossible to distinguish from everyone around you, yes. But the same principle, the same physics, the same quiet accumulation of microseconds that, given enough velocity, enough altitude, enough difference from a reference frame, adds up to something detectable, something a clock can hold. The Hafele-Keating numbers were small enough that they almost weren't detectable with 1971 instruments. Almost. The error bars were wide. Some physicists at the time were skeptical not of relativity, but of whether the measurement precision was tight enough to be meaningful. Those objections were fair. They were good faith scientific skepticism, the kind the process needs. But the experiment was repeated, multiple times, with better clocks, with GPS satellites doing it continuously, automatically, at a scale of engineering rather than curiosity. Each repetition narrowed the uncertainty. Each one came back saying the same thing with increasing precision. The prediction holds. The clocks behave exactly as a relativistic universe requires them to behave. At a certain point, skepticism becomes stubbornness. The measurements are real. The world is that world. And yet the thing about measuring time so precisely, so obsessively, with instruments that would lose 1 second across 30 million years, is that it keeps revealing how much we don't control. Every correction the GPS system makes is an acknowledgement, an admission, a small engineering act of humility that says, we built our system assuming time was constant, and it isn't, and so we adjust. And we adjust again, and we will keep adjusting because the universe does not simplify itself for convenience. There's something almost philosophical in that. Or maybe it just feels that way at this hour. The clocks flew, they landed, they told the truth in nanoseconds about the nature of time, and the truth was that time is a local thing, yours specifically, determined by your speed and your position, and the gravitational field pressing down on whatever chair or bed or floor you happen to be in contact with right now. It curves, it slows, it accelerates. It never quite does what you'd expect if you hadn't been told, but it moves forward, always that, always only that so far. Space bends. That's where this starts. Not with time, not yet, but with the shape of space itself, which is not the neutral, flat, featureless container most of us carry around in our heads. It curves, it warps, it responds to mass the way a heavy object responds to the surface it's placed on, which is an analogy so overused it's almost useless. But the underlying fact remains, space is not rigid. It has a geometry, and that geometry is not fixed. It is a living thing in the sense that it changes, that it reacts, that it is shaped by everything moving through it. General relativity, Einstein's 1915 theory, the deeper and stranger successor to special relativity, is at its core a theory about that geometry, about how mass curves space-time, and how that curvature tells matter how to move, and how that movement in turn influences the curvature. A closed conversation between matter and shape that never quite resolves, never reaches a steady state, just continues, locally, everywhere, all the time. What nobody fully anticipated when Einstein published those equations was what some of them would permit. A Scottish physicist named Willem van Stockum was working through the mathematics of a very particular hypothetical object. An infinitely long, incredibly dense cylinder, rotating, just spinning. That's the whole setup. A cylinder of matter, rotating fast enough that the centrifugal tendency outward is balanced exactly by the gravitational pull inward. A stable, spinning column of mass stretching, in the mathematics at least, without end in both directions. Van Stockum solved Einstein's field equations for this object, and what the equations gave back was a spacetime geometry with a specific, uncomfortable property. If you were to fly a spaceship around this cylinder close enough at the right angle, the path you trace through spacetime would curve, not just through space, through time as well. You would orbit the cylinder and arrive back at your starting point, not only in the same location but at an earlier moment, before you left. The equation said this, not as an error, as a solution. Van Stockham didn't make much of it, from what I can tell. He noted the geometry, published the mathematics, moved on. Maybe he thought the infinite cylinder was too unphysical to worry about. Maybe he just filed it. The paper existed. The solution existed. And for a while it sat there in the literature the way old journal papers do, slightly yellowed at the edges even in their digital forms, waiting for someone to come back to it. Kurt Gödel, logician, mathematician, a man with a reputation for finding the precise crack in any structure he examined, turned his attention to general relativity. He was, at the time, a colleague of Einstein's at Princeton. They walked together, they talked, and Gödel apparently wanted to give Einstein something for his 70th birthday. What he gave him was a universe. Gödel found a solution to Einstein's field equations describing an entire cosmological model, a universe filled with rotating matter, spinning slowly on a large scale. In this universe, the rotation of matter drags spacetime with it, and the dragging accumulates over distance, and what accumulates is a geometry that allows, permits, mathematically requires, paths through spacetime that loop back on themselves. Closed time-like curves. You could travel in Gödel's universe through space, and if you went far enough and came back you would arrive before you departed. Not sort of before, not approximately before. Einstein apparently found this disturbing. The detail is almost too good to be true. The man whose equations enabled the result, reading the result and being disturbed by it. He said so, he wrote about it. He believed our universe probably didn't rotate in the way Gödel's model required, and he was right about that. Our universe, as far as observation can determine, does not rotate on a large scale. But Gödel's solution was valid. It was a legitimate answer to legitimate equations, and that was the problem that didn't go away. Here's the thing about general relativity that makes this more than a collection of exotic footnotes. The field equations are not a single equation. They're a system. 10 equations, interlinked, describing how the curvature of spacetime relates to the energy and momentum of whatever matter is present. You feed in a description of matter and energy, and the equations give you back the geometry of spacetime. And because the equations are flexible, because they don't pre-impose a shape on spacetime, the range of solutions they admit is vast. Most of the solutions describe familiar things: spherical masses, orbiting bodies, expanding space, black holes. These are the solutions that match what we observe, that have been tested and confirmed and used to make predictions that held. But some solutions describe things we haven't found, things that might not exist anywhere in the universe. And among those solutions, sitting quietly alongside the Schwarzschild metric and the Friedmann equations and all the well-behaved geometry of the observable cosmos, are solutions that contain closed time-like curves, space-time paths that loop. The equations don't forbid them, they find them, produce them, hand them back when the right matter configuration is supplied. The Tipler cylinder is one of these. Frank Tipler worked it out in the 1970s, taking Van Stockham's infinite rotating cylinder and making the case more explicit. Rotate the cylinder fast enough, make it dense enough, and the spacetime outside it develops the looping geometry. A ship flying a helical path around the cylinder close enough at the right pitch could trace a closed time-like curve, could return to its own past. The catch, and it is a considerable catch, is the word infinite. The cylinder has to be infinitely long, not very long, not impractically long, infinite, because it turns out that a finite version of the same cylinder, same density, same rotation rate, just with two ends instead of none, doesn't produce the time-looping geometry. The infiniteness is doing structural work in the mathematics, holding together a spacetime that a finite version can't sustain. Which means the Tipler cylinder is, as a practical matter, impossible to build. Not difficult, not expensive. Impossible. You cannot construct an infinite object. There isn't the matter for it, and there isn't the space, but it's still a valid solution. The equations still produce it. And a valid solution to general relativity is a description of something that spacetime can in principle be shaped like. Whether it is somewhere out there in a universe we can't fully map, that's a different question. Then 1988 arrived, and Kip Thorne opened something he probably couldn't close. The paper was framed innocuously enough. It was about wormholes, Einstein-Rosen bridges, shortcuts through spacetime connecting two distant points. The concept wasn't new. The bridge structure had been in the literature since the 1930s, but wormholes had always been assumed to be unstable, to collapse before anything could pass through, to require conditions so exotic they effectively ruled themselves out. Thorne and his colleagues looked at this more carefully. They asked what it would take to hold a wormhole open. What kind of matter, with what properties, would be required to stabilize the throat? And the answer they got was negative energy density. Matter with essentially a negative energy, stuff that pushes spacetime outward rather than pulling it inward, that would prop the wormhole open the way a doorstop holds a door. Negative energy density. It sounds impossible. The kind of phrase that appears in science fiction next to words like flux capacitor. But quantum field theory actually permits it, in the small quantities, under specific conditions. The Casimir effect, where two metal plates placed very close together experience a measurable attractive force because of quantum fluctuations in the vacuum between them, involves negative energy density in a real, measurable way. The effect is tiny, the amounts are tiny, but the principle is there. What Thorne's paper did was establish that there was no fundamental law of physics prohibiting a traversable wormhole, just severe engineering constraints, just the problem of gathering and stabilizing enough negative energy to hold a mouth open. Just that. And if you have a traversable wormhole, you have, under certain conditions, with one mouth accelerated and then returned to the other, a time machine. I want to be careful here, because it's easy to let the momentum of the argument carry further than the physics actually goes. None of this means time travel is possible. Not the Van Stockham solution, not Gödel's rotating universe, not Tipler's infinite cylinder, not Thorne's wormhole. None of these are confirmed to exist in nature. The solutions are real. The structures they describe may not be. There is a difference, a meaningful, non-trivial difference between mathematically permitted and physically realized. The equations permit a lot of things. They permit solutions we've never observed, geometries that would require conditions the observable universe may simply never produce. The fact that a thing can be written down without contradicting any known law is not the same as the fact that the thing exists. But here is the part that I keep finding difficult to quietly set aside. The equations don't forbid it. General relativity, our best description of gravity, of space-time geometry, of the large-scale structure of the universe, does not contain a line that says no loops, no line that says time must flow in one direction only, no prohibition built into the geometry. The forward flow of time is built into our experience, into thermodynamics, into the way entropy accumulates and structures dissolve, but it is not built into Einstein's field equations. The equations don't care which way you go. They describe paths through space-time. They don't rank them by direction, which is something. I'm not sure what to call it exactly. Not permission, not encouragement. Just a kind of absence of refusal that is harder to dismiss than it might first appear. Hawking thought the universe would step in. That quantum effects near the formation of any time-looping geometry would build up into an energy catastrophe, a cascade of vacuum fluctuations amplifying themselves into a kind of automatic demolition, destroying the loop before it could be used. He called it the chronology protection conjecture, and he named it with a tone that was half conviction and half dry humour. The idea that the laws of physics conspire to keep the universe safe for historians. It's a good conjecture. It might be right, but it is still just a conjecture, unproven, dependent on a theory of quantum gravity that doesn't fully exist yet. So the situation as it stands is something like this. The equations of general relativity produce solutions with time loops. Those loops require exotic or infinite conditions. Hawking believed quantum mechanics would forbid them even then, but nobody has proven Hawking right. And nobody has found one. And the universe is large. The universe is old, and we have seen very little of it. Van Stockham worked it out in 1937 and didn't make much of it. Gödel handed it to Einstein as a birthday present, and Einstein was unsettled. Thorne put it in a journal in 1988, and the conversation has never quite recovered. The math is still there, patient, not waiting for anything in particular, just sitting in the solutions the way a shape sits in a set of equations, real in the only sense that mathematics is real, which may or may not be the same sense that the physical world is real. That question, whether mathematical existence implies physical existence, is old enough to have its own philosophical subfield. I'm not qualified to resolve it. I'm not sure anyone is. What I know is that the equations don't say no. And in the dark, at this hour, that feels like a more interesting answer than it probably should. There's a version of this story where it starts with a phone call. Carl Sagan, novelist, astronomer, television presence, a man who took the public appetite for the cosmos more seriously than most of his colleagues thought was strictly necessary, was writing a science fiction novel in the mid-1980s, Contact. He wanted his protagonist to travel between stars, and he wanted the mechanism to be physically plausible, or at least not physically embarrassing. He'd used a black hole in an early draft, and someone told him that wouldn't work, that the tidal forces would be catastrophic, that the geometry was wrong for transit. So he called Kip Thorne. Thorne was, at that point, one of the most respected relativists alive. Caltech, decades of work on gravitational waves, black holes, the deep structure of space-time. Not a man who spent much time on science fiction consulting, presumably, but he thought about it. And then he thought about it more seriously. And what started as a favour for a novel became, by 1988, a paper in Physical Review Letters, one of the most prestigious journals in physics, with Thorne's name on it, making a careful and technically rigorous case that traversable wormholes were not, as far as general relativity was concerned, forbidden. That's how the door opened. A novel, a phone call, a physicist who got curious and couldn't stop. I want to say something about what it means that the paper appeared where it did. Physical Review. Letters is not a speculative publication. It's not a place for thought experiments dressed up as science, not a venue for interesting if true proposals that haven't been worked through. Papers there are peer-reviewed, mathematically rigorous, expected to meet a standard that takes years to learn how to meet. When something appears in that journal, the physics community treats it as a serious contribution, not necessarily correct, not necessarily describing something real, but serious, worth engaging with, worth arguing against if you disagree. Thorne's wormhole paper was serious. That was, in a way, the whole problem. Because what the paper said, carefully, with all the appropriate qualifications, with the mathematics laid out in full, was that a wormhole with a traversable throat was consistent with general relativity, provided you could supply the right kind of matter to stabilize it. The right kind being matter with negative energy density. Matter that, in the classical sense, doesn't exist in usable quantities. But, and this is the part that made the paper harder to dismiss than it might otherwise have been, matter whose underlying quantum mechanical behavior permits negative energy states in principle. The Casimir effect. Squeezed light. Effects that are real, measured, reproducible in a lab. Thorne wasn't saying here is how to build a time machine. He was saying something more uncomfortable than that. He was saying, I cannot find a law of physics that prohibits this. There's a difference, it matters. If a physicist says we don't know how to do this yet, that's one kind of statement. Technology problem, engineering problem, give it time, give it resources, maybe it gets solved. But if a physicist says I cannot find a reason this is forbidden, that's different. That's a statement about the structure of reality, about what the laws, as we currently understand them, permit. And when that statement comes from someone at Thorne's level, with Thorne's rigor, in a journal with that publication standard, it lands differently than it would coming from anywhere else. The physics community couldn't just ignore it. Some tried, some wrote responses arguing that the exotic matter requirements were so extreme as to be effectively impossible, which is probably true, and Thorne acknowledged as much. Some pointed out that a traversable wormhole once created would almost immediately face stability problems from quantum fluctuations, radiation. The sheer difficulty of maintaining a macroscopic exotic matter structure in a universe that tends toward equilibrium. All fair, all probably correct. But nobody found the fundamental prohibition. Nobody came back with a proof that the equations themselves rule it out. The responses were engineering objections, not physics objections, and that distinction is everything. Now, the time travel part. This is the piece the 1988 paper didn't lead with, and I think that's worth noting actually, because it would be easy to assume the paper was primarily about time travel and dressed up in wormhole language. It wasn't. The time travel implication was a consequence, derived later by Thorne and colleagues in a follow-up. The logic goes roughly like this. If you have a traversable wormhole, two mouths connected by a throat allowing passage in either direction, and you take one of those mouths on a journey at high speed and then return it, time dilation acts on the travelling mouth. The travelling mouth ages less than the stationary one. When you bring them back together, the two mouths are now at different points in time relative to each other, and a wormhole, we'll call, is a shortcut through spacetime. Not just through space, but through spacetime. Step through the mouth that has aged less, and you emerge from the mouth that has aged more. You've gone backward. Not maybe. Not in a hand-wavy sense. In the same sense that the Hafele Keating clocks ran at different rates, by the same physics, the same time dilation, the same geometry. Just applied to the mouths of a wormhole instead of a clock on a plane. The mechanism is clean. The physics is consistent. The matter requirements are absurd, but the mechanism is clean. I've spent time, probably too much time, trying to identify the moment in Thorne's thinking where this became unavoidable. where the wormhole paper stopped being about exotic matter and stable throats and started being about what you could, in principle, do with one. I don't know when that moment was. No, wait, that's not quite right. I don't know if there was a single moment. These things tend not to arrive as moments. They arrive as slow accumulations of implication, each step individually small until you look up and realize you've walked somewhere unexpected. What I do know is that by the early 1990s, Thorne was writing about time machines directly, not hiding the implication inside wormhole geometry, writing about it in academic papers with his name on them, acknowledging that if the wormhole proposal was sound, the time travel consequence followed necessarily. He also, to his credit, spent significant effort trying to find the reason it was wrong. Collaborating with Stephen Hawking, thinking seriously about the chronology protection conjecture, trying to identify the quantum mechanical process that would destroy any incipient time machine before it could be used. He wanted, in some sense, to close the door he'd helped open. He didn't manage it, not fully. The conjecture remains a conjecture. Here's what the paper actually is, stripped of everything. 60-odd pages. The journal version is much shorter, but the full technical treatment is longer, of dense mathematics describing the properties of a hypothetical space-time structure. The kind of thing that sits in a university library in a bound volume of physical review letters from 1988, slightly yellowed at the edges, the kind of paper where the equations occupy more space than the prose. You could hold it. It has a weight. The paper itself is just paper, just ink, just the physical record of a thought someone had. But what it did to the conversation around time travel in physics is, it legitimized the question. It moved the discussion from the fringes to the center. It made it okay, professionally okay, career survivably okay, for serious physicists to work on these problems without being dismissed. That's not nothing. Science has sociology the way everything else has sociology. Ideas need permission to exist in certain spaces. Thorne's paper gave the time travel question permission to exist in the space where serious physics happens. Whether anything real follows from that permission is still open. The wormholes haven't been found. The exotic matter hasn't been gathered in the quantities required. The chronology protection conjecture hasn't been proven, but then neither has it been defeated. The situation 37 years after the paper was published is almost exactly where it was the morning after. No closer to a machine, no closer to a hoof of impossibility. Just the question, sitting in the literature, serious and unresolved. I find that I'm trying to think of the right word and I keep landing on strange. Not frustrating, not exciting exactly, just strange. That a question this large can sit in the professional literature for nearly 4 decades without being answered in either direction, without a discovery that closes it and without a proof that disposes of it. The door opened. Nobody walked through. Nobody has managed to close it. It just stays open. The frame is solid, the hinges are good, and on the other side the mathematics just sits there in the dark, patient and unverified, waiting for something. Maybe nothing ever comes. Maybe something does. Either way, the door isn't going anywhere. He set a table. That's the whole experiment, really. A table. Champagne in an ice bucket. Proper champagne, the good kind, not the sort you open because it's Tuesday and why not? Balloons, a banner. The specific optimism of a party that expects guests. Stephen Hawking held this party on June 28, 2009, in a room at Gonville and Caius College, Cambridge. He sat. He waited. Music, apparently. He had music playing. And he waited for a considerable length of time in a decorated room with chilling champagne and the quiet hum of preparation, for guests who would never arrive. Nobody came. The design of the experiment is almost too elegant to have been accidental, which makes me suspect it wasn't. The invitations, formal, printed, complete with coordinates and local time, were sent out only after the party had ended, after the champagne had gone warm, after the balloons had begun their slow surrender to gravity. The logic being, a future where time travel exists is a future where someone could receive that invitation and come back. The party would be the proof. The guests would be the data. No guests, no data. Hawking wrote about it afterward with what reads as dry satisfaction, the satisfaction maybe, of a man who expected a specific outcome and got it. He said he'd sat there a long time. He said the empty room felt like empirical evidence. He was, in that sentence, doing something between a joke and a serious argument, and I'm still not entirely sure which weight he meant it to carry. There's a version of that afternoon I keep returning to, not the physics, not the logical structure of the test, just the room, the sound of a party that isn't happening, the way champagne smells when it's been open for an hour and nobody's drinking it. Not quite sour, not quite sweet. Something between the two, something that smells specifically like expectation going stale. The banner probably slightly askew, Hawking in his chair, the music he'd chosen playing into the empty space with the particular indifference of music that no longer has an audience. There is something in that image that I find not soured exactly, something more specific than sad. The word that keeps coming is patient. Like the experiment itself was an act of patience. He set the conditions and he waited, and the universe gave its answer in the form of an empty chair that stayed empty. He was not the first. In 2005, a graduate student at MIT named Amal Durai held a convention for time travelers, advertised it, spread the word as widely as he could, in the explicit hope that word would spread forward through time and someone would come back. He wanted to be generous with the logistics, gave a precise location, a precise date, made attendance as frictionless as a convention for time travelers could reasonably be. Nobody came to that one either. Then Hawking, 2009. Then a team of physicists at Michigan Tech who searched the internet, which we'll get to. But that's a different kind of experiment, a different texture of negative result. What stays with me about the party specifically is that it was personal. It wasn't a search, it wasn't a database query. It was a man setting a table and sitting down and waiting. There's a human quality to that which the internet search doesn't have. An investment, a specific afternoon, given over entirely to the question of whether the future would respond. It didn't. Or, and this is the part of the argument that is easy to skip past, maybe it responded in the only way available to it. Hawking himself noted this. The absence of time travelers doesn't prove time travel is impossible. It might just mean that the past, our past, this specific era, isn't interesting enough to visit. Anyone capable of travelling back in time has, presumably, the whole of human history available as a destination. Why here? Why a party in Cambridge in 2009? Why not something more historically significant, more visually arresting, more worth the journey? There's also the possibility, more technically serious, that time travel to the past can only go as far back as the moment the first time machine was activated. If a working time machine is built in the year 2400, the earliest moment reachable from that machine is 2400. You can't go further back than the machine's creation, which would mean that even if time travel is invented, eventually in some distant future we can't see from here, nobody from that future can reach us. We're upstream of the machine. We're too early. We wouldn't appear on any tourist's itinerary, not because we're unimportant, because we're inaccessible. That's a genuinely strange thing to sit with. The idea that we might be permanently sealed off from the future, not because the future doesn't exist, not because time travel never happens, but because we fall on the wrong side of a technological threshold that hasn't been crossed yet. History from the future's perspective looking back might contain a clear dividing line. Before the machine, unreachable, after, visitable. And we are before. Every person alive right now. Every moment happening on this planet tonight. All of it. If the threshold theory is right, permanently unavailable to anyone born after the machine is built. Like a city that existed before the records began. You know it was there, you can't visit it. The champagne at Hawking's party went flat. The music played. The balloons held their shape for a while and then stopped holding it. The banner stayed where someone had hung it. The ice in the bucket became cold water and then became room temperature water, and at some point someone came in probably and tidied up, put things away, folded the banner. The question the experiment asked didn't get answered. It just got absorbed into the record, into the long list of things we've tried that the universe responded to with quiet. Hawking called it empirical evidence. He was probably right that it's evidence of something. Whether that something is impossibility or inaccessibility or simple lack of interest, or the upstream of the machine problem, that part he left open. The evidence is the absence. The interpretation of the absence is still ours to make. There is something honest about an experiment that can't be published in a journal. You can't submit an empty guest list to physical review letters. You can note it. You can describe it. But the absence of a thing isn't data in the way that the presence of a thing is data. It can't be graphed. It doesn't have error bars. It is a room that was arranged for guests who didn't come, and the best you can do is report the arrangement and the emptiness as faithfully as possible. Hawking did that. He reported it with a kind of precision that was almost affectionate. The date, the tour, the champagne, the balloons, the specific duration of the wait, the stillness of the outcome. The experiment was, in its own way, a perfect thing. Not because it answered anything, because it asked the question in the most direct possible form and let the universe respond in kind. The universe said nothing, which is either the clearest answer physics has ever given on the subject of time travel or the most ambiguous one. Probably both, at the same time. That feels right somehow for a question about time. Imagine you went back, not how, just that you did. Some mechanism, some geometry, some configuration of matter and spacetime that we haven't built and may never build, but suppose it existed and you used it, and you arrived. Some moment before this one, a room you recognize, a version of the world that has not yet become the version you left. What would you do? Most people ask this question, have an answer ready, something they'd change, someone they'd warn, a decision they'd unmake. The question almost pulls the answer out of you. The mind goes immediately to the revision, to the correction, to the specific thing that could be different if you had access to its before. But here's the problem. Here's the thing that Novikov spent years turning over, that a 1990 paper co-authored by some of the most careful minds in theoretical physics eventually tried to formalize into a principle. You might not be able to, not wouldn't, might not be able to. There's a difference, and the difference is the whole weight of this chapter. Igor Novikov, Soviet astrophysicist, a man who thought about time travel with the same methodical patience you'd apply to orbital mechanics or stellar evolution, arrived at a position in the mid-1980s that sounds, on first hearing, like something from a myth. The position is this. Any trip backward through time that could create a paradox has a probability of 0. Not low probability. 0. The universe does not permit events that contradict themselves, and therefore anything a time traveler does in the past was always going to happen, has always been part of the history that led to this moment, cannot be otherwise because otherwise it would contradict the record that already exists. You could go back. You would do exactly what you did. You are always going to. The first reaction most people have to this is resistance. Mine was, the idea feels like a trap disguised as a principle, as if someone took the problem of paradoxes and instead of solving it just declared the paradoxes illegal, probability zero, off the table, no further questions. It seems like it's doing something philosophically suspect, using the desired outcome as a premise. But that's not quite what Novikov was doing. Or, I think that's not what he was doing. Let me try to be more careful. The Novikov self-consistency principle is grounded in a specific mathematical observation about closed time-like curves. In a spacetime that contains a time loop, the laws of physics, not rules someone invented, but the actual dynamical equations governing how matter and energy behave, only admit solutions that are globally self-consistent. When you work through the equations describing what happens on a time loop, the inconsistent scenarios don't just fail to occur. They fail to be solutions. They are not low probability paths. They are not paths at all. The mathematics simply doesn't produce them. This is different from saying the universe forbids paradoxes by fiat. It's saying that in the geometry of a time loop, the only physical histories that can exist are the ones that are already consistent with themselves. The equations enforce consistency not as a rule imposed from outside, but as a property of what counts as a valid solution. Whether that's more reassuring or more disturbing, I genuinely cannot decide. The paper that formalized this, the 1990 paper, Novikov and several colleagues, including Thorne, used a mechanical test case. A billiard ball fired into a wormhole mouth at an angle calculated to send it back in time and knock its earlier self away from the wormhole, preventing it from entering in the first place. The paradox in compact form: the ball enters because it entered, but also doesn't enter because it was knocked away. What the mathematics found when two students at Caltech worked through the actual trajectories was that there are self-consistent solutions. They are not the obvious ones, they are not the simple paths you'd first draw, but they exist. The ball goes in, the ball comes back, the ball delivers its earlier self at a glancing impact, enough to deflect slightly, not enough to prevent entry. The result is consistent, not tidy, not intuitive, but consistent. The ball always gave itself that glancing blow. It was always going to. The trajectory was always that specific, odd, slightly off path that keeps everything coherent. What the ball couldn't do was knock itself completely clear. The probability of that outcome, in the self-consistent framework, is exactly zero. Not small, zero. It's not a path the physics permits. Now take that billiard ball and replace it with a person. This is where it gets, I want to say uncomfortable, but that word is doing too much work. It's more specific than uncomfortable. It's the specific feeling of reaching for something and noticing your hand was already moving. The sensation of an action you thought you were choosing that turns out to have been, in some sense, already determined. Not by fate, not by God, not by some external mechanism, by the geometry of the situation itself. If the Novikov principle holds, a time traveler can do things in the past. Real things, meaningful things, things with consequences, but not things that contradict the record, not things that prevent their own trip, not things that erase the causes of what already happened. The space of available actions is real but bounded. You can move within it. You cannot step outside it. Novikov himself addressed the free will question directly, and his answer was, characteristically I think, more practical than philosophical. Physics already restricts your free will every day, he noted. You cannot will yourself to fly, you cannot walk through a wall. Gravity and condensed matter physics constrain your actions continuously, and you do not generally experience this as an assault on your autonomy. You simply accept that some things aren't available to you. The consistency constraint on a time traveler, he argued, is no different in kind, just different in which actions it removes from the available set. I've read that argument several times. It's logically sound. It doesn't fully settle the unease. Part of why it doesn't settle is the question of what it would feel like from the inside. If you went back, or in a Novikov consistent universe, and tried to prevent something and failed, you would experience that failure as just that. A failure. Bad luck, wrong timing, something got in the way. You wouldn't experience the constraint as a constraint. You'd experience it as circumstance. The universe would arrange through ordinary-seeming physical processes for your attempt to come to nothing, for the intervention to fall short, for the thing you were trying to prevent to happen anyway. And you'd have no way of knowing whether you failed because of chance or because consistency required it. This is and I'm aware this sounds like I'm reaching almost a description of ordinary life, the number of times you've tried to change something and failed, and couldn't be sure whether the failure was contingent or necessary, whether a different attempt at a different moment might have succeeded, or whether the outcome was always going to be the outcome. I'm not saying those things are the same, they're not. But there's a texture to the Novikov picture that feels less alien than it initially seems. The principle has a significant assumption built into it, which Novikov acknowledged, and which matters for how much weight to give the argument. It assumes a single timeline, one history, no branching, no parallel tracks, no separate universe that splits off when you interfere with the past. If multiple timelines are possible, if going back and changing something doesn't create a paradox, but instead creates a fork, then consistency isn't required because the change happens on a branch that doesn't connect back to the original. You can kill the grandfather on the branch. Your original timeline still contains you, still runs forward, still leads to the moment you stepped into the machine. Novikov's principle is explicitly incompatible with the many worlds approach. It requires a universe with one history in which the past is fixed, in which going back means going back to the past, not a past. Which picture is correct, single timeline or branching, is not settled. It may not be settleable with current physics. The answer probably lives somewhere in a theory of quantum gravity that doesn't fully exist yet, which means it lives somewhere we can't reach from here. So the situation the Novikov principle leaves us in is something like this. If time travel to the past is possible, and if the universe has a single timeline, then the principle is almost certainly right. Not as an imposed rule, but as a mathematical consequence of what self-consistent solutions look like in a looping spacetime. And if it's right, then anyone who's ever travelled back has done so without disrupting anything, has acted in ways that were always part of the record, has been, from the perspective of someone standing in their past and watching them, just another person doing just another thing, unremarkable, ordinary, already accounted for. Which raises a question the chapter isn't going to answer. How would you know? If a time traveller from the future were here, in this era, in this period of history, doing whatever the consistency equations allow them to do, there would be no anomaly to detect, no paradox to notice, no visible seam in the record. Everything they did would already be part of what happened. Everything they changed would already have been changed. The history we know, the one we're living in, would already contain their presence. We would have no way to see them, not because they're hiding, because they're consistent. This is either a loophole or a locked room, depending on where you're standing when you look at it. Novikov's principle solves the paradox problem by absorbing it entirely, There are no paradoxes because paradoxical events have zero probability, and zero probability means they simply don't occur. Clean, rigorous, mathematically defensible. But the solution has a quality that I find, I keep wanting to say elegant and keep stopping myself because elegant isn't quite the right word. It's more like airtight in a way that makes you want to check the seams. Every exit is closed. Every paradox is dissolved before it forms. Every attempt to change the past either succeeds in a way that was already part of the past or fails in a way that was always going to fail. You can go back. You just can't go back and make it different. The room is locked from the inside, and you're already in it. In 2010, 2 optical atomic clocks were placed approximately 1 meter apart vertically in a laboratory at NIST, the National Institute of Standards and Technology in Boulder, Colorado. One clock sat roughly a foot higher than the other. Same room, same building, same city, same elevation, nearly the same everything. They ticked at different rates. The higher clock ran faster, by a tiny amount, 37 billionths of a second over the course of 1 billion seconds, which is itself already a number that resists casual understanding. But the difference was there, measured, repeatable, confirmed. Gravity, at 1 foot of separation, is doing something to time that instruments can now detect. The clocks responsible for this are called optical lattice clocks, and they are, I want to be careful not to oversell this, but there is no non-dramatic version of what these instruments do, the most precise timekeepers ever built by human hands. They work by trapping atoms in a lattice formed by intersecting laser beams, then interrogating those atoms with light at a specific frequency and measuring the response. The atoms oscillate. They oscillate at a rate so stable, so indifferent to temperature and vibration, and the ordinary chaos of a working laboratory, that the clock can track a second to within a few hundredths of a femtosecond, a unit of time so small that light, moving at 300,000 kilometers per second, travels roughly 30 nanometers in one of them. The clocks don't hum, they don't tick audibly. The lab around them has a specific quality of stillness, not silence exactly, more like silence that someone has worked very hard to manufacture and maintain, where the absence of vibration is itself an achievement. They just run, quietly, exactly, now. The 2010 result was striking, but it was followed 14 years later by something that made it look almost rough. In 2024, a team at Gödel, also in Boulder, the same general ecosystem of precision physics, used an optical lattice clock to measure gravitational time dilation across a distance of less than a millimeter. Submillimeter. We are talking about the width of a human hair, or slightly less, as the vertical separation over which the time difference was detected. The width of a hair, 2 clocks, different rates, not different by much. The difference at submillimeter scales is almost insultingly small, a number so far past the decimal point that writing it out would be mostly zeros before you reached any other digit. But the measurement found it. The instrument, built with enough precision, held long enough, isolated carefully enough from every source of noise and interference, found the signal into the data. Gravitational time dilation exists at the scale of a human hair. Let that sit for a moment, because I think it's easy to read that sentence and nod, and move past it without fully absorbing what it requires. Einstein's general relativity predicts that time runs slower in stronger gravitational fields. The surface of the Earth is a stronger gravitational field than 1 millimeter above the surface of the Earth, barely by an amount so slight it took the most precise instruments ever built to detect it. But the prediction is exact, not approximate. The theory gives a specific number for how much slower, and the experiment found that number, within experimental uncertainty, at scales smaller than anything you could see with the naked eye. This is not a metaphor for something. It's not an analogy or a useful simplification. It is a literal description of what time does in the physical world you inhabit. The air above your kitchen counter is, by a completely unmeasurable in daily life but entirely real amount, moving through time at a slightly different rate than the counter itself. I keep finding myself wanting to describe what this means in some larger sense, and then stopping, because I'm not sure it means anything larger. It might just be what it is. A property of the universe, measurable now at scales we couldn't reach before, precise and unglamorous and real. But there is something in the progression, from Hafele and Keating flying clocks around the world in 1971, to NYST measuring it across a foot in 2010, to Gödel measuring it across a hair in 2024. That feels less like a series of confirmations and more like a closing in. Each experiment shrinks the scale at which the effect is detectable. Each one brings the measurement closer to the human body, to the scale of cells, eventually, theoretically, to distances at which biological processes occur. We're not there. The clocks precise enough to detect time dilation at cellular scales don't exist yet. But the direction of travel is clear. The astronaut Scott Kelly spent 340 days on the International Space Station at an orbital altitude of roughly 400 kilometers. When he returned, his body had physically aged slightly less than his twin brother Mark, who stayed on the ground. The difference was tiny, fractions of a millisecond, not years, not even seconds. But it was there, biologically measurable in fact. NASA ran detailed studies on both men. They found differences in gene expression, in telomere length, in dozens of physiological markers. Most of those differences were from the space environment, radiation, fluid shifts, microgravity effects on the body. Teasing apart the pure time dilation contribution from everything else was not straightforward. But the clocks don't lie. The physics is the same physics that NIST measured across a foot and JILA measured across a hair. Scott Kelly moved through time at a different rate. His cells, for 340 days, experienced a fractionally different flow of time than his brother's cells on the ground. He time-travelled, barely, into the future, by being somewhere that time ran slightly differently. The thing I find myself turning over, and I'm not sure this goes anywhere productive, but it keeps surfacing, is what it means that we're measuring smaller and smaller separations and still finding the effect. There's an implicit question lurking in that progression. If the effect is detectable at a hair's width now, and the precision of our instruments keeps improving, at what scale does time dilation stop being a property of separated objects in space and start being a property of a single object's internal structure? At what point does a single human body, which has a top and a bottom, which exists across a vertical range, which has a head at one height and feet at another, contain within itself a measurable time difference between its own parts? Probably we are not there. The numbers at biological scales are almost certainly below any measurement threshold we can currently reach. But the question has a shape to it that feels different now than it would have before 2024. Less hypothetical, less distant. The 2024 measurement required extraordinary effort to achieve. The vibration isolation, the temperature control, the laser stabilization. The sheer duration of data collection needed to accumulate enough signal to separate the real effect from the noise. The people who built this did so knowing that a positive result would confirm something already expected. General relativity is not a theory that has been giving unexpected results at these scales. The experiment was not going to overturn anything. It was going to measure something that was always there. That's a different kind of science from the kind that discovers. It's the kind that looks closer. That takes what we know is true and asks how small the scale at which it's true still goes. And the answer in 2024 was smaller than a hair. Smaller than we'd directly shown before. Maybe the next result will be smaller still. Maybe someone in a lab in Boulder or Tokyo or Delft is running an experiment right now, in the dark, in the engineered stillness, with lasers interrogating atoms at frequencies no human ear can detect, that will push the measurement to a new minimum. Time dilation, one laboratory at a time, keeps turning out to be more present than anyone needed it to be. More here, more now, more. In the ordinary fabric of the room you're in, the body you're in, the particular height above sea level of whatever surface is currently beneath you. It was always running. These measurements don't make it more real, they just make it harder to hold at arm's length. Robert Nemiroff is an astrophysicist at Michigan Technological University who, in 2013, did something that required either a very particular sense of humor or a very particular kind of earnestness. Possibly both, in proportions that the paper itself doesn't quite reveal. He searched the internet for time travelers, not casually, not as a thought experiment or lecture illustration, as a genuine study with a methodology, with co-author Teresa Wilson, with a specific logical framework and a set of search terms chosen for their uniqueness, and with results that were submitted, unsuccessfully it turns out, to 3 peer-reviewed journals before the paper found its way onto Archive, where it has been sitting ever since, available to anyone, cited occasionally, treated by the physics community with the particular mixture of acknowledgement and gentle distance reserved for work that is technically serious and also kind of impossible to place. The design of the search is worth understanding because it's smarter than it sounds. The problem with looking for time travelers on the internet is immediately obvious. Anyone who travelled from the future would presumably know not to leave traces, or would have been warned, or would be operating under some set of rules, cultural or physical or governmental, that prohibits interference with the past. The obvious objection writes itself, but Nemiroff and Wilson were looking for a specific and narrower thing, not deliberate disclosure, but accidental leakage. The kind of thing that happens not because someone wanted to be found, but because they slipped, mentioned something they shouldn't have known yet, searched for something before it existed. They needed events with names that were completely new, terms that couldn't have appeared in any text before a specific date, because the thing those terms described didn't exist before that date. 2 candidates emerged. Comet Ison, discovered September 21, 2012, named for the telescope network that found it, a name with no prior usage, no ambiguity, nothing else it could refer to. And Pope Francis, a name that entered the world's vocabulary on March 16, 2013, when Jorge Mario Bergoglio chose it, the first pope ever to use it, a name that had never appeared in that context before that morning. The logic: find either of those phrases in any text, tweet, search or query, or post that predates those moments, and you have something worth looking at. They search Twitter, Facebook partially, harder to search reliably, timestamps less trustworthy, the architecture of the platform not built with forensic historical queries in mind. Google Trends, which offered aggregate data on search volume but couldn't surface individual queries. The web more broadly, with all the caveats about misdated pages and cached content, and the general unreliability of timestamps across a system that was never designed to function as an archive. Twitter turned out to be the most reliable venue, because tweets can't be backdated. The timestamp is assigned at posting and isn't editable. If a tweet containing Comet Ison or Pope Francis existed before those terms had any business existing, it would be there. No such tweet was found. Not one. The researchers were careful to note this precisely. No clearly prescient content involving either term was located in any tweet, ever. They widened the search and asked potential time travelers to actively identify themselves by tweeting specific hashtags before a deadline that hadn't been announced yet. Nobody did. Some tweets arrived after the request was made public, one of them reading with a quality that is either deeply sincere or deeply deadpan. Your future laws forbid me from giving you any proof of our technologies, but be sure that we're watching you. Which is, honestly, that's a perfect response. It covers every base. It can't be disproven. It's also not evidence of anything except someone having a reasonable amount of fun with the premise. The results section of the paper contains a sentence that I've read several times, each time finding it slightly different in tone depending on my mood. No clearly prescient content was found. 5 words of conclusion after a genuinely elaborate search. The flatness of it is either anticlimactic or exactly right. Nemiroff himself told a reporter that he hadn't really expected to find anything. He knew it was unlikely, but, and this is the part that interests me, he also said he wasn't aware of anyone having conducted a search like this before. Which means the reason nobody had done it wasn't that it was known to be pointless. It was that nobody had bothered. There's something in that. The willingness to construct a serious methodology for a question that most people wouldn't take seriously enough to formalize. The acknowledgement that absence of evidence is not evidence of absence, but that a careful search for a specific signal is still worth doing, even if the signal probably isn't there. That's a particular kind of scientific temperament. Slightly stubborn, a little bit, I want to say romantic, but the paper's prose style does not support that reading. What the search couldn't account for is in some ways more interesting than what it found. A time traveller who knew history, who came from a future with records of this era, would presumably know about the search, would know the dates, the terms, the methodology, and could simply not use those terms before those dates. Not because of any physical constraint, just awareness. The same awareness that would prevent you from mentioning in a letter written in 1985 an event that didn't happen until 1993. You just wouldn't. Not because you couldn't, but because you'd know better. This is the fundamental problem with searching for careful time travelers. Their carefulness is exactly what would make them invisible. The search was, in a sense, designed to catch the careless ones, the ones who slip, who forget, who don't realize that a specific combination of words didn't exist yet. And those, if they exist at all, apparently didn't make it into Twitter's public record between the early 2000s and mid-2013. Or they did, and deleted it. The paper notes this possibility directly. Content once posted can be removed. Prescient tweet that existed for 20 minutes before its author realized the mistake and deleted it would leave no trace in a 2013 search. The other constraint, the one that Hawking's Empty Party also runs into and that Nemiroff acknowledged, is the machine creation threshold problem. If time travel to the past can only reach as far back as the moment the first machine was built, then no search conducted before that moment will find anything. We're upstream. The earliest point any future traveller could reach is the moment the technology exists, and if that moment is in the future, possibly the distant future, then this era, this internet, these tweets are all permanently inaccessible to anyone who might want to visit them. Not interesting enough to visit, not worth the trip, or not upstream of the threshold, sorry, the other way. Too far upstream, too early. The machine doesn't reach this far back. I keep getting turned around by that framing. Forward and backward feel intuitive until you're actually thinking about temporal mechanics, and then the directions start to swim a little. The paper was rejected by 3 journals. Nemiroff mentioned this openly, with what reads as cheerful resignation rather than bitterness. The reasons for rejection aren't public. Peer review doesn't typically publish its deliberations, but it's not hard to imagine the difficulty. The methodology is sound, the execution is careful, the result is genuine, but the subject sits at an angle to normal scientific publishing. It's not physics in the usual sense, it's not astronomy. It occupies a strange interstitial space between a rigorous null result and a thought experiment in a piece of public engagement that happened to use the apparatus of academic research. Arxiv took it. It lives there now. Anyone can read it. It's been cited in discussions of time travel, in popular science writing, in occasional academic papers that deal with the epistemology of absence. How you know something isn't there, how you construct a valid search for a null result, what it means to look carefully and find nothing. Nothing in this case being the operative word. The internet, searched as carefully as 2013 allowed, contained no evidence of time travelers, no prescient tweets, no anachronistic search queries, no hashtag sent from before the hashtag was invented. The record of this era, at least the publicly searchable, algorithmically accessible portion of it, looks exactly like what it would look like if time travelers don't exist, or can't reach this period, or are careful enough not to leave traces, or operate under rules that prohibit interference, or some combination of all of those that shifts depending on which theoretical framework you're standing in. The null result is real. It's just not conclusive. It's the same quality of silence as the empty room at Cambridge, the same shape of absence. A search conducted, evidence not found, the question still open in exactly the way it was before the search began, except now there's a paper documenting that someone looked, that the looking was serious, that the nothing is a known and recorded nothing, not just an assumed one. That might seem like a small thing. For a question this size, it might be the best available. There is a question that physicists rarely ask out loud in quite this form, and I want to try to ask it carefully because the careless version of it sounds like speculation dressed as inquiry, and the careful version is, I think, genuinely worth sitting with. The question is not whether time travel is possible. That question has been asked repeatedly in the preceding chapters, and in the literature, and in lecture halls, and in the popular imagination for longer than general relativity has existed. The question I want to ask is quieter, more specific. It is this: what would it actually mean for physics to forbid something? Laws of physics are not laws in the legislative sense. They were not prohibitions issued from some authority and enforced by a mechanism. They're descriptions, the most accurate and compressed descriptions we have of how the universe behaves, distilled from observation and experiment and mathematical reasoning over centuries. When we say a law of physics forbids something, what we mean, carefully stated, is in every situation we've tested, in every experiment we have run, in every corner of the universe we've been able to observe, this thing does not occur, and our best mathematical description of reality is consistent with it never occurring. That's a strong statement. It's not a weak one, but it's not the same as an absolute prohibition built into the fabric of existence. It's a description of what has been observed, extended carefully, with appropriate uncertainty, into a claim about what can be. When those descriptions are incomplete, when there are known gaps between theories, when two of our best frameworks for understanding the universe are mutually inconsistent in specific regimes, the strength of the prohibition weakens, not to nothing, not to anything goes, but to we don't fully know. Here is where general relativity and quantum mechanics sit with each other, and I want to be precise about this because the imprecision is often where the confusion starts. General relativity describes gravity, space-time, geometry, the large-scale structure of the universe. It is extraordinarily well tested. The predictions it makes about gravitational waves, about the bending of light near massive objects, about the expansion of the universe, about black hole behavior, have been confirmed to remarkable precision. It is one of the most successful physical theories ever constructed. Quantum mechanics describes the behavior of matter and energy at very small scales. It is also extraordinarily well tested, arguably the most precisely verified theory in the history of science, prediction matching experiments to 10 decimal places in some cases. The quantum framework has been confirmed in every laboratory test it has ever faced. These two theories are incompatible, not slightly in tension, not awaiting a minor reconciliation. Fundamentally, structurally incompatible. They use different mathematical languages, make different assumptions about the nature of space and time, and when you try to apply both simultaneously in regimes where both should matter, near the center of a black hole, at the moment of the Big Bang, at the smallest scales of spacetime, they produce infinities. Nonsense. Results that cancel each other out rather than combining into a coherent description. The theory that would reconcile them, quantum gravity, does not exist yet, not in complete form. String theory, loop quantum gravity, causal dynamical triangulations. These are attempts, some more developed than others, none of them confirmed by experiment, none of them universally accepted. This is the gap. This is where the answer to the time travel question might be living. Hawking's chronology protection conjecture, the argument that the laws of physics conspire to prevent time machines from forming, is based on a specific physical mechanism. The argument goes roughly like this. Near the formation of any closed Timelike curve, quantum vacuum fluctuations would pile up, amplifying through the loop again and again, building into a catastrophic divergence of energy density that would destroy the nascent time machine before it could be used. The universe, Hawking suggested, self-destructs any incipient time loop through a kind of automatic quantum feedback. It's an elegant argument. It's physically motivated to poussard. It uses real quantum mechanical effects, not invented ones. And it points in a direction that feels intuitively right to many physicists who have spent time thinking about the problem. But, and this is the part that doesn't go away, the calculation that supports it requires semi-classical gravity. It uses quantum field theory applied to curved spacetime, which is an approximation technique, not a fundamental theory. It works well in many regimes. It breaks down at very high energy densities, and the divergence that's supposed to destroy the time machine occurs precisely at the scale where semi-classical gravity stops being reliable, where the Planck scale physics kicks in, where quantum gravity would take over, where we don't have a complete theory. The calculation runs up to the edge of what our mathematics can handle and then stops. Right there, at the exact moment when the answer would be given. I want to be honest about what I find this genuinely frustrating in a way that feels different from ordinary scientific uncertainty. Most open questions in physics have a clean shape. We know what we don't know. We have instruments being built, experiments being designed, theoretical frameworks being extended. The gap has a defined perimeter. This gap doesn't, quite. The theory that would tell us whether the chronology protection conjecture is actually enforced by quantum gravity is the same theory we don't have yet. The answer sits behind a door that the entire field of theoretical physics has been trying to open for 60 years. Not time travel specifically. The door is the unification problem, how gravity and quantum mechanics fit together, and time travel is just one of the questions waiting on the other side of it. So when someone says the chronology protection conjecture is probably right, which many physicists do, including careful and serious ones, what they mean is, It's consistent with what we know, and it's physically motivated. It points in a direction that the intuitions of the field support, but the proof requires tools we don't have. The conjecture is a reasonable bet, not a theorem. There is a difference. It matters. The honest accounting of where we stand looks something like this. General relativity permits closed time-like curves under specific conditions. Those conditions are extreme, requiring infinite rotating cylinders, or traversable wormholes held open by exotic matter, or the kind of large-scale universal rotation that observation strongly suggests our universe doesn't have. So the opportunities for time loops may simply not arise in the universe as it exists, regardless of whether they're prohibited. Separately, Hawking's conjecture suggests that even if the geometric conditions were met, quantum effects would destroy the loop before it could function. This argument is physically serious but technically incomplete. It depends on a semi-classical calculation that breaks down exactly where the answer matters most. And separately again, Novikov's self-consistency principle suggests a third possibility. Loops can exist, but only self-consistent ones. No prohibition, no destruction, just a universe in which paradoxical histories have zero probability, and consistent ones are the only solutions the equations produce. 3 different answers, each one technically defensible, each one contingent on assumptions about quantum gravity that nobody has confirmed. All 3 sitting in the literature simultaneously, politely unresolved. The footnote feeling comes here. The sense that you've followed the main text carefully and arrived at a footnote that is larger than the chapter that contains it. Because what the incompleteness between general relativity and quantum mechanics really means, for this question, is that the prohibition we'd need to definitively rule out backward time travel, the actual hard limit, the proven law rather than the motivated conjecture, would have to come from the unified theory, from quantum gravity, from a mathematical framework that can handle both the geometry of spacetime and the quantum behavior of matter simultaneously at all scales without breaking down. That theory doesn't exist yet. When it arrives, if it arrives in a form that makes testable predictions, one of the things it will presumably settle is whether closed time-like curves are genuinely forbidden or merely difficult, whether the universe enforces chronology or simply makes violation impractical, whether Hawking was right that the physics conspires to protect the timeline, or whether Novikov was right that the timeline is its own protection, or whether there's a third answer neither of them reached. Right now, sitting at this gap, the honest answer to what the equations say about time travel is, they don't say enough. Not because the question is unanswerable in principle, but because the framework from which the definitive answer would come is still being built. Which returns me to the question I started with. What does it mean for physics to forbid something? It means our best current description says this doesn't happen and has been tested sufficiently that the confidence is high. For some things, faster than light travel of information, violation of conservation of energy, the spontaneous unmixing of a dissolved substance, that confidence is extremely high, resting on deeply confirmed theoretical foundations with no known exceptions. For backward time travel, the confidence is different. The equations that would forbid it cleanly aren't complete yet. The experiments that would confirm the prohibition haven't been designed, because the effect they'd need to detect occurs at scales we can't currently reach. The theoretical consensus leans toward impossibility, but leans is the operative word. It hasn't arrived. The silence in the math is where the interesting things live. Someone said something like this to me once, about a different problem, and I've been carrying it around for years. Not because silence is the same as permission, it isn't, but because unexamined silence can be mistaken for a wall when it might just be a room nobody has entered yet. The room is still there, Nobody has gone in. We don't know what's inside, and the equations for now are quiet about it. Scott and Mark Kelly are identical twins. Same DNA, same parents, same childhood in New Jersey, same path through the Navy into NASA's astronaut program. They flew in space together, separately on different missions, and for years their biological profiles tracked closely enough that researchers who studied them found the similarity useful as a baseline. Two people who started, genetically speaking, from the same place. In 2015, Scott went to the International Space Station and stayed. Not for a typical increment, as the standard rotation is roughly 6 months, but for 340 days, nearly a year, a continuous year, which at that point was the longest single spaceflight any American had completed. Mark stayed on Earth, went about his life, did the things a retired astronaut does, and while Scott orbited at roughly 400 kilometers above the surface, moving at about 28,000 kilometers per hour, the two men, who had begun as biological near copies of each other, began very quietly to diverge. NASA knew this was happening. That was partly the point. The twin study, a formal research program involving dozens of investigators across multiple institutions, was designed to measure exactly what a long-duration spaceflight does to the human body, using Mark as the control, the unchanged reference, the version of Scott Kelly that stayed behind. Blood draws at regular intervals, cognitive assessments, gut microbiome sampling, telomere length measurements, gene expression profiling. The study generated 10 papers, eventually coordinated into a single publication in Science in 2019, and it is, in the unglamorous tradition of good science, meticulous, edged, careful, and genuinely remarkable. The results were complicated. Space does a lot of things to a body simultaneously, and pulling apart which effect came from which cause is not clean work. Radiation exposure, fluid shifts from microgravity, the body's blood pools differently when there's no down. Disrupted circadian rhythms, altered immune function, psychological stress. The researchers were careful to note that isolating any single variable was difficult, and that many of the changes observed in Scott reversed after he returned, and that the ones that didn't weren't necessarily permanent. But running underneath all of it, quieter than the gene expression data and the microbiome shifts and the cognitive test scores, was the physics, the simple, unambiguous, already proven physics of time dilation. Scott Kelly for 340 days was moving faster than Mark Kelly. Not dramatically faster. The orbital velocity of the ISS is high by everyday standards, but a tiny fraction of the speed of light, and the time dilation at that speed is correspondingly small. He was also at higher altitude, where gravity is weaker, which runs time in the opposite direction, slightly faster rather than slower. The two effects partially cancel as they do for GPS satellites, but not completely. The net result, Scott Kelly's clocks, his atomic clocks, his cellular clocks, his biological clocks, ran at a marginally different rate than his brother's for almost a year. The difference in raw time amounts to a fraction of a millisecond, not a second, not a minute. A fraction of a millisecond accumulated over 340 days of continuous difference in velocity and altitude. This is not enough to see in a mirror. It is not enough to feel. Scott Kelly did not return from space looking younger than his twin in any way a camera could capture. The difference is real and is physically there, and is completely invisible to every instrument the human body contains. But it is there. The physics doesn't care that it's small. The physics just runs the numbers and says, these two men, who began at the same point in time, are no longer at the same point in time. One of them moved through time at a marginally different rate. One of them, measured against the other, is fractionally younger than he would have been had he stayed on the ground. I want to stay with the biology for a moment, because it adds a layer that the physics alone doesn't have. Telomeres are the protective caps at the ends of chromosomes, sequences of repeated DNA, that shorten slightly each time a cell divides, functioning as a kind of cellular age counter, a biological record of how many divisions a cell has undergone. In most circumstances, shorter telomeres correlate with cellular aging. This is not a perfect measure. It's noisy, influenced by many factors, but it's a real one, and it's been the subject of enough research to be taken seriously as a physiological marker. During Scott Kelly's year in space, his telomeres got longer. Temporarily. They extended during the mission, and then shortened again after his return, and within 6 months were back to roughly the same length as before. The researchers were cautious about interpreting this. Telomere extension in space is poorly understood, and the reversal complicates any simple narrative. But the observation is there. The body, under the conditions of spaceflight, did something unexpected with its cellular timekeeping machinery. Was this time dilation? Almost certainly not at the cellular scale. The physics says the effect at ISS velocities and altitudes is far too small to produce measurable biological change. The telomere shift was almost certainly from other causes: radiation, microgravity physiology, stress response. But the coincidence of languages is hard not to notice. Cellular clocks and atomic clocks, both running differently in space for different reasons, producing different kinds of divergence from the earthbound baseline. The body as a timekeeping instrument, ticking at rates set by its environment. He came back on March 1st, 2016. The Soyuz capsule landed in Kazakhstan in the dark, in the cold. The step in early March has a specific quality of cold that isn't dramatic but is thorough, the kind that finds the gaps in clothing. And Scott Kelly was helped out of the capsule by recovery crews because, after 340 days without gravity, a body doesn't simply resume walking. The muscles have been working against nothing for almost a year. The vestibular system has recalibrated for an environment where there is no down. The cardiovascular system has redistributed fluid upward because the body adapted to a world that wouldn't pull it toward the feet. The reassertion of gravity is, by multiple accounts, a strange physical experience. The sudden weight of the arms, the specific heaviness of the head, the body's own mass, which in orbit became largely abstract, returning all at once as a concrete and demanding fact. He stood eventually, walked, was photographed squinting in the cold with the Kazakh steppe behind him, and he was, by a fraction of a millisecond, by a margin too small to measure with anything that existed in that recovery zone, by an amount that required not a ruler but a careful theoretical calculation to confirm, younger than his twin brother than he would have been had he not gone. He had, in the most literal sense available to us without exotic matter or traversable wormholes or rotating infinite cylinders, travelled in time. The thing that I find myself returning to at home then, and this is personal in a way that I'm not entirely sure how to justify, is not the physics of what happened to Scott Kelly. The physics is clear and well established, and I've thought about it enough that it sits quietly now without needing examination. What I keep returning to is Mark. Mark Kelly, on the ground, going about his life for 340 days while his genetic near copy orbited overhead. Running slightly ahead of Scott in time, in the only meaningful sense time dilation gives us, aging marginally faster. Accumulating experience at a marginally higher rate, being pulled slightly further ahead along the timeline by the simple fact of standing on the surface of a planet. Not knowing, probably not thinking about it, the tiny temporal distance opening between them. There is something in that. Two identical people, same starting point separated by a few hundred kilometers of altitude, and the physics that altitude implies, drifting apart in time by an amount smaller than any clock in that kitchen could measure. The gap between them is real, and the gap is undetectable, and the gap is exactly the kind of gap that becomes visible only when you have the theory to know what to look for. This is what time travel looks like when it's real and confirmed and completely ordinary. Not a portal, not a flash of light or a spinning machine or a dramatic displacement. A man in a spacecraft, moving fast at altitude, for a long time, coming home slightly younger than the version of himself that stayed, being welcomed back by a brother who is, by a margin no instrument on Earth could directly measure, technically older than the physics says he should be if they had stayed together. The scale of it is almost offensive. All that mathematics, all that theory, all that careful derivation, and the result, in human terms, is a fraction of a millisecond across almost a year of difference. But the direction is right. The mechanism is right. The physics is the same physics. It's just that the numbers, at the speeds and altitudes available to us, are small. Scale the velocity up. Scale the duration up. Keep the same mechanism running, unchanged, just more of it. And the millisecond becomes a second. The second becomes a day. The day becomes something you'd notice when you came back through the door. We can't do that yet. The speeds required are beyond anything we've built. But the principle is not hypothetical. The principle is sitting in the medical data of a NASA study, documented in science, in the cells of a man who came back from orbit and stood in the cold in Kazakhstan and was, by the same physics that runs every GPS satellite over your head, a very small distance ahead of where time said he should be. He walked back through the door, and on the other side of it, time had moved slightly differently than it had for him. That's not a metaphor. That's a measurement. Those aren't the same thing, and they don't need to be. Start here. A path through space-time that returns to where it began. Not near where it began, not approximately, not within a useful margin, exactly. The same coordinates in space, the same coordinates in time, the same event in the fullest sense of that word, which in physics means a specific location in 4 dimensions with no ambiguity about which one is meant. You leave a point. You move through space-time. You arrive back at the point you left, at the moment you left it. This is what a closed time-like curve is, not a loop in space, not an orbit, not a circle you draw on a map. A loop in space-time, a path that closes not just in 3 dimensions but in 4. The mathematics permits this. We've established that. General relativity in specific solutions produces space-time geometries that contain these paths. The conditions required are extreme. The solutions may not describe anything that actually exists in the observable universe, but the geometry is valid, the mathematics is sound, and what I want to do in this chapter is not revisit whether the loop can exist. We've been through that, but instead try to stay inside it long enough to understand what existing on one would actually mean. This is harder than it sounds. The mind wants to approach a closed time-like curve from outside, to treat it as a diagram, a topology problem, an interesting feature of a mathematical space. That's the natural move. It's also, I think, the move that prevents you from feeling the full strangeness of the thing, because the strangeness isn't in the shape. It's in what the shape would do to the experience of being a person moving through it. So, you are on a closed time-like curve. You don't necessarily know this. That's the first thing to establish, and it matters. There is no internal signal that tells a traveller they're on a loop. Your proper time, the time measured by your own biological processes, your own clocks, your own subjective experience of duration, runs forward, always forward. The loop doesn't reverse your experience of time. It bends the path of your time back toward its starting point without reversing the direction of travel along that path. Think of it this way, and then let me immediately qualify this, because the analogy is imperfect in a specific way that matters. Think of the surface of the Earth. You walk in a straight line as straight as you can manage, and eventually you return to where you started. You were always moving forward. The surface curved beneath you. You didn't feel the curvature at any individual step. The return was a global property of the geometry, not a local property of any moment's experience. A closed time-like curve is something like that, except the geometry is space-time rather than a sphere's surface, and the thing that returns to its starting point is not just your position but your when. The direction of your personal time, forward, always forward, moment following moment in the only sequence consciousness knows, brings you eventually back to a moment that already happened, that you already lived, or will live, or are living. The tenses stop working. Here is where identity becomes a physics problem rather than a philosophical one. If you complete a closed time-like curve and return to the event you started from, you are, physically, into terms of your position in space-time, at the same location as your earlier self, the same four-dimensional point. And your earlier self is there too, beginning the loop you just finished. Two versions of you at the same space-time event, one arriving and one departing. Are they the same person? The later version has the memories of the loop. The earlier one doesn't have them yet, or rather, has them as a future that hasn't happened yet, which on a time loop means a future that is simultaneously the past. The later version knows what happens on the loop because they just lived it. The earlier version is about to live it for what feels like the first time. But if the Novikov self-consistency principle holds, if the only physically realizable histories are self-consistent ones, then the earlier version will live exactly what the later version remembers. The loop is not a sequence of events that happened once and will happen again. It is a sequence of events that is always happening, in the sense that there is no temporal vantage point from which you could say it happened and is now over. The loop is a structure in space-time. It doesn't play once and stop. It simply is, the way a ring is, not cycling but closed. Memory on a loop is, this is where I feel least certain about whether I'm saying something meaningful or just generating sentences that sound meaningful, so I want to flag that uncertainty before continuing. Memory on a loop is strange in a specific structural way. Your memories of the loop would be memories of events that are, from the perspective of the loop's geometry, always occurring. Not memories of a past. Memories of a structure. The thing you remember didn't happen and then stop happening. It is part of a closed path in space-time that has no before or after in the global sense, only a local sense of sequence experienced by the person moving along it. There is a feeling, probably everyone has had some version of it, of a memory whose origin you can't locate. Something that feels like a recollection but has no identifiable first moment. No scene in which you learned it or experienced it, just the knowledge sitting there, with no clear temporal address. I'm not claiming this is related to time loops. I'm not suggesting anything mystical, but I find the texture of that experience useful as an approximation for what it might be like to remember something that, by the geometry of your situation, never had a first occurrence. Let's try to go deeper into the experience. Stay with it. You're moving through the loop. Your experience is sequential for breakfast, then a walk, then a conversation, then whatever the loop contains. Moment following moment in the only order experience permits. You're not experiencing the loop as a loop, and you're experiencing it as a life, or a segment of a life, moving in the only direction a life moves. At some point, And this is the part the mathematics doesn't fully specify, because the mathematics describes the path but not the phenomenology of travelling it. You arrive back at the beginning. And here is where I genuinely don't know how to think about what happens. The Novikov principle says you do what you did. You take the actions you took. You say the things you said. Not because something external forces you to, but because those are the only self-consistent solutions available, and physical reality only realizes self-consistent solutions. Does it feel like free will? Novikov says, the same way it always feels, every action you take anywhere feels like free will. The consistency constraint isn't different in kind from gravity's constraint on your ability to fly. You don't feel gravity as a prohibition, you just can't fly. And the reason sits in the physics rather than in your experience of trying. A person on a time loop doesn't feel constrained. They just do what they do. What they were always going to do, what they specifically in the specific configuration of the universe at that moment were the kind of person who would do, which may or may not be different from ordinary life. I keep getting uncertain about that distinction. Causation on a loop has a texture that is difficult to hold steady in the mind for long. Ordinarily, causation is a sequence. A causes B causes C. The arrow points forward. You can trace any event back to the events that produced it, and those events back further, in a chain that extends into the past without looping. The asymmetry of the chain, the fact that causes precede effects, that A comes before B rather than after, is so fundamental to the way we experience and describe the world that it functions less like a fact and more like the medium in which facts exist. On a closed time-like curve, the chain closes. A causes B causes C causes, eventually through some number of steps, A. The cause is also the effect. Not in a mystical sense, not in a hand-wavy sense, but in the precise sense that the same event sits at both ends of the chain, and the chain is not a chain but a ring. And a ring has no beginning. You can start reading it anywhere. Any point is as valid a starting place as any other. This is not a paradox within the Novikov framework. It's a closed causal structure, self-consistent, self-supporting, every event entailed by the events that follow from it, which are also the events that precede it. The philosopher in the room would call it a causal loop with no first cause. The physicist would call it a self-consistent solution to the equations of motion on a spacetime containing a CTC. Both descriptions are accurate. Both descriptions leave something out. I'm not sure what either of them is leaving out exactly, but the feeling of incompleteness is real, and I've decided to trust it rather than paper over it. Here is what I keep returning to, late in the chapter, the way you return to a paragraph you've already read twice because it doesn't quite yield what you thought it said. If closed time-like curves exist somewhere in the universe, in the vicinity of some exotic matter configuration, or near the throat of some naturally occurring wormhole or in some geometry we haven't yet identified, then somewhere in the universe these loops are not a thought experiment. They are structural features of space-time. They are just there. And anything, any matter, any light, any information that finds itself on one of those paths is on a curve that closes, moving through what it experiences as forward time, forward sequence, forward cause and effect, moving from the perspective of a wider space-time map along a ring that has no temporal outside. Whether any person, any observer, any entity capable of experience has ever been on such a path, we don't know. We have no evidence that such geometries exist in the accessible universe. We have no evidence they don't. The observable universe is a sphere roughly 93 billion light-years in diameter, and we have looked carefully at a very small fraction of it. If someone is on a loop right now, if some structure somewhere contains a closed time-like curve with something moving through it, that something doesn't know. It's just moving. forward, through what it experiences as a sequence, approaching from its own perspective a future that is also, from the geometry's perspective, its own past. And the loop just holds the way a ring holds, not because something is maintaining it, because that's what closed things do, they stay closed. The room is the same room it was an hour ago. Same walls, same dark, same particular quality of nighttime quiet that isn't quite silence. A building settling, something outside moving briefly and then not. The specific texture of a late hour that has been going on long enough to feel permanent. You're still here. That's not nothing. It keeps striking me at the end of these long nights with a physics problem that the most verifiable fact in the room is also the easiest to overlook. You're present. You're located in a specific point in space-time, this room, this moment, and you're moving through time at a rate determined by your altitude above the Earth's surface, your velocity relative to other reference frames, the local curvature of space-time produced by the mass of the planet beneath you. You don't feel any of that. You just feel the dark and the quiet, and whatever the bed or the chair or the floor is doing to the parts of you in contact with it. We've covered a lot of ground tonight. Or not ground exactly. Ground implies a surface that holds still while you move across it. What we've covered is more like water. You move through it, it closes behind you, and the question of where you've been becomes a question of what you remember rather than a question of where you can point. Time dilation is real. Measured, woven into the infrastructure of the world you navigate daily, silently corrected for in every device that needs to know where you are. The clocks on the planes in 1971 confirmed it. The clocks in orbit confirm it continuously. The width of a hair is enough separation for the effect to exist. Backward, harder. The math doesn't say no. The math produces loops in specific geometries under conditions so extreme they may never arise in the accessible universe. Maybe. Hawking thought the universe would step in and prevent them. He couldn't prove it. Novikov thought the universe would allow them but only the consistent ones. He couldn't prove it either. The question sits between those two positions, unresolved, patient, waiting for a theory of quantum gravity that is still being assembled somewhere, in offices and on whiteboards and in papers being revised right now by people who don't yet know if their approach will work. Hawking sat at a table. That keeps coming back. A decorated room, champagne going warm, the specific silence of no one arriving. The man who did more than almost anyone alive to map the theoretical structure of time, sitting in a room that time had emptied. There's no clean interpretation of that image. It's not proof of anything. It's not even a good argument. Formally speaking, the absence of party guests doesn't demonstrate the impossibility of time machines any more than a missed bus demonstrates the non-existence of public transit. But it has a weight to it that the formal arguments don't. Something about the human scale of the gesture, the specific patience of waiting for something that, if it came, would rewrite everything. It didn't come. He tidied up, presumably. The champagne got put away, the banner came down, and we're still here, still in this era, this period, this band of history that, if the machine creation threshold argument is right, is permanently upstream of any time travel technology. Inaccessible from the future, not because we're unimportant, because we're too early. There might be something quietly comforting in that, depending on how you hold it. This moment, or this specific hour, this particular night, whatever is outside your window right now, might be genuinely unreachable from any point in time beyond a certain threshold. Not archived, not visitable, not a destination anyone with a working time machine will ever choose or be able to choose, just here, occurring, unrepeatable in the way that only things that can't be revisited are unrepeatable? I've been thinking about this question for a long time. Longer than this script, longer than this project. The question of whether time travelers are among us is one of those questions that sounds like it belongs to science fiction until you follow it carefully into the actual physics, at which point it stops belonging to science fiction and starts belonging to a set of open problems in theoretical physics that nobody has solved yet, and that may require a fundamental breakthrough to approach. What I've found, following it this far, is not an answer. What I've found is a cleaner version of the question. Not, is backward time travel possible? But, what would it mean for physics to fully prohibit something it currently only suspects is prohibited? Not are time travelers here, but what would their presence look like if it were required by the self-consistency of the loop to be invisible? Not, did Hawking's empty party prove anything? But what kind of evidence could this question ever in principle admit? Those are better questions than the ones I started with. That's usually how it goes with physics. You come in with the popular question, the vivid, speakable, late-night version, and you leave with something more precise and less answerable and somehow more interesting. The precision is a kind of progress, even when it doesn't move you toward resolution. 3 of us built this. Every chapter, every draft, every hour in the research that turned into a single quiet sentence you almost didn't notice. No algorithm deciding the topics, no studio paying the bills. If tonight was worth something to you, if the dark feels a little more textured than it did an hour ago, there's a way to help keep this going over on Patreon. It's genuinely what makes the difference between the next script existing and not existing. And if you're watching rather than listening, if the subscribe button is somewhere on this screen, and if you want more nights like this one, that button is the most direct way to make sure they keep arriving. Leave a comment too if something here stayed with you. We read them. All of them. More carefully than you'd probably expect. Matthew and Brian have been with this project long enough to have heard things that no longer exist in any published form. Early drafts, discarded ideas, the versions of these scripts that didn't make it. That kind of sustained presence it's genuinely what keeps a self-funded project like this from collapsing under its own uncertainty. We're grateful for it in a way the word grateful doesn't quite reach. The room is quieter now than it was at the start. Not because anything changed, because you've been in it long enough for the quiet to feel like yours. Time is still running, through you, around you, at the specific rate this altitude and this latitude and this velocity assign to this body in this moment. Forward, the only direction experience has ever actually known. Whether anyone has ever found another direction. Whether the equations that permit it describe something real or something merely mathematical. Whether Hawking's empty table meant what he thought it meant or something else entirely. The question stays open. It was open before tonight. It's open now. The opening is the same shape, just more visible, more familiar. The kind of open you can sit with rather than push against. Outside, the world is doing whatever it does at this hour. Inside, you're still here, and time, indifferent and structural and quietly astonishing, is still passing, at its own rate, as it always has.